Have you heard that people who contract COVID do not produce long-lasting antibody defenses against COVID, thereby potentially increasing risk of reinfection? I know that's counterintuitive from what we've learned about viruses, because most of the time when you are infected with a virus, you produce antibodies that then confer long-lasting protection. Well, today I want to cover science that helps us understand why we don't develop long-lasting protection in COVID, thus far at least, in early 2021 with the studies that we have to date. Also, I want to discuss why science has found an increased induction of autoimmune disease in people with severe COVID cases. So people who contract COVID and have a severe case have higher induction of autoimmunity from COVID-19. So we want to discuss those two topics today because there's a similar physiologic mechanism driving that. I'm Dr. John Bartemus, and I'm putting the pieces together to help you live a life at optimum. To understand why people don't produce long-lasting antibody defense against COVID-19 or the SARS-CoV-2 virus, we have to first understand how long-lasting antibody defenses are developed in a normal immunological situation. By first understanding that, we can then understand why it doesn't happen in COVID, and we can also understand why severe COVID infection induces autoimmune disease in certain people. So, if you're infected with SARS-CoV-2 virus, you're going to have a certain cascade of immunological events. If you're infected with or exposed to any other antigen, normally you're going to have antibody production, long-lasting antibody development. So let's cover that and then cover the SARS-CoV-2 or the COVID response. So let's start with an antigen. And an antigen, hold on, the purple marker doesn't work. Let's lose it. Okay, we'll use blue for the antigen. So an antigen is a fancy term for something exposed to the immune system, something foreign. It could be food, it could be a virus, it could be anything basically foreign. Okay, it doesn't even necessarily have to be a bad thing. It could be a bad thing like a virus or a cancer cell, but a strawberry is an antigen in the GI tract. So let's use an infectious antigen for this example. So we have an antigen, and what happens is in our immune system we have what are called dendritic cells, and they have spidery looking arms here, and a dendritic cell is going to pick up that antigen and head to the lymph node, okay? And in the lymph node, the dendritic cell is going to present the antigen to a T cell. So not having that purple really hurts me because I need it. So I'll make a T cell with blue as well. So we have a T cell that receives antigen, receives the handoff from the dendritic cell, and at this point the T cell is naive, meaning it could be anything. It could differentiate into anything. So a naive T cell is a young child, say, and it has to mature into an adult, and as an adult it can pick whatever career it wants, right? So when the dendritic cell presents to this T cell, it's presenting the antigen to it, but then it's also secreting certain cytokines or certain chemicals to influence the growth or development of that T cell, or to influence the career it wants to pick. All right, and in regards to antibody production, the T cell class that drives antibody production are called T follicular helper cells, or TFH cells. Okay, so and the chemical that promotes development of a T follicular helper cell is called interleukin 21. So we have interleukin 21 here, and so this T cell matures into what's called a T follicular helper cell, or a TFH cell. And very key for that to happen, we need a transcription factor called BCL6. So the combination of BCL6 and interleukin 21 will promote T follicular helper cell development. I know this sounds like a lot of science jargon, but it's going to make sense later when we show you how the research is showing us why these things are happening. Okay? So then the T follicular helper cell has the opportunity to present antigen in the interfollicular zone of the lymph node. The T follicular helper cell can present antigen to a B cell. And B cells are part of the antibody response. So the T follicular helper cell presents to a B cell, and from the interfollicular zone here, the B cell can either enter the B cell follicle and go to the germinal center and mature appropriately, or it can mature extrafollicularly, so outside the B follicle, and enter the bloodstream. Okay, so if it doesn't enter the follicular center, the B cell follicle into the germinal center, it will be an extrafollicular B cell. And that extrafollicular B cell goes back to the blood to have its effect. Okay, so an extra, we'll say BE for extrafollicular. An extrafollicular B cell now can go back into the blood and have a short-term antibody response, or it comes right away. It has an acute antibody response, but it's short-lived, okay? And this is what's called a low affinity response. So it's not as specific to the antigen as it could be if it had matured in the germinal center. And we're gonna circle back to this, but there's certain checkpoints that B cells go through in maturation. Okay, so while we're on that topic, checkpoint number one is right here in the interfollicular zone. Checkpoint 2 for proper maturation occurs in the B cell follicle, and then checkpoint 3 occurs in the bone marrow here. So remember that, we're going to return to that. Extrafollicular B cell ramps up right away, goes and has a response, but it's a lower affinity, not as specific. All right? If we have the B cell enter the B cell follicle into the germinal center, we now have follicular B cells. Okay? It's this follicle or group of them. And in the germinal center, follicular B cells meet with, what color do I have there? So we'll have a B cell that meets up with germinal center T follicular helper cells. And these cells talk, and this is going to be a follicularly matured B cell, so B follicularly matured. And so this one has gone through checkpoint 1. This one has gone through checkpoint 2. And it's been matured to be a follicular B cell, and that B cell has potential for long life, long-lasting antibody defense for us. So that one leaves the lymph node and goes back to the blood, and that can become a memory B cell, or what's called a plasmablast. And plasmablasts mature into, they can enter the bone marrow and mature into what's called long-lived plasma cells. And long-lived plasma cells are what confer long-term antibody response, antibody defenses, long-term immunity. They're there, and if we're re-exposed, they can produce more antibodies for us if we need more, in addition to the memory B cells that are out in the blood waiting for second exposure. Okay? And both of these will produce what's called a high affinity response to the antigen. So they will be, affinity is how specific they bind the antigen, recognize it, take care of it. So follicularly matured B cells have high affinity response and result in long-lived plasma cells, so long-term antibody defenses and memory cells. Whereas extrafollicularly matured B cells have a low affinity, they don't bind as specifically, they don't result in long-term antibody response. So you could have an infection, have an antibody response, but because it's not long-term, if you're only extrafollicular, down the road we test and oh, your antibodies are negative, so you're more susceptible for second infection there. Okay, makes sense? So this is what happens in normal B cell production antibody response to an antigen. Now, why does COVID not result in long-term antibody response? Well, research is showing there's multiple points in this chain that result in poor production of long-term antibody response and promote autoimmunity. And one of those spots here is I need a different color. So let's use black. Okay? So, what researchers are finding is that patients with COVID infection, especially severe COVID infection, they have lower levels of T follicular helper cells. They have blockages in BCL6. So they aren't able to differentiate into T follicular helper cells. So we have, if we have blockage of the transcription factor to produce these, we're of course going to have lower levels of these. If we have lower levels of T follicular helper cells, we have lower levels of germinal centers in these people and germinal center T follicular helper cells, which results in not production of memory B cells, of plasmablasts, and non-production of long-lived plasma cells. So we don't have development of long-term immunity, antibody defenses. And so what we're left with are the extrafollicular matured B cells. And remember, the extrafollicular cells didn't go through the checkpoints. They maybe hit checkpoint 1, but they didn't hit 2, and they didn't hit 3. Well, why is that important? Well, these checkpoints, as the B cell is maturing, it has to reach these checkpoints. And at these checkpoints, the body is looking for what are called autoreactive B cells. And autoreactive B cells are B cells that recognize self-tissue, recognize me, recognize you, okay? And autoreactive B cells, if allowed to enter the circulation, are now looking for me or looking for you, looking for self-tissue. And if they find that, they mark that for destruction, and that's called autoimmune disease. So lacking proper BCL6, T follicular helper cells, germinal centers, lacking proper maturation and reaching the checkpoints increases risk and probability of extrafollicular B cells, which haven't met those checkpoints, developing into autoreactive B cells that then drive autoimmune disease. And this is the mechanism that is believed to be happening in COVID-induced autoimmunity. So this explains both. Extrafollicular B cell maturation explains why we don't have long-lived plasma cells and long-lived antibody defenses, and increased extrafollicular B cell maturation explains COVID-induced autoimmunity because they haven't gone through the checkpoints to eliminate those potentially autoreactive B cells. So I hope this makes sense. If it didn't, play it back. Obviously, lay people don't necessarily need to know this, but I think it's important for clinicians to understand this so we can answer questions from our patients that say, hey, why aren't I developing antibodies? I've had COVID. What's my risk for second infection? Or, why am I having these autoimmune symptoms after after I suffered from COVID, even though I recovered from it? This is the physiology that the science up to date at this point in January 2021, this is what the science is showing us. And so if this interests you and autoimmune disease interests you, I've written an Amazon #1 best-selling book called The Autoimmune Answer. And I invite you to read that. And in that book, I cover more immunology, cover autoimmune disease, cover specific autoimmune diseases like psoriasis and pandas and celiac disease and Hashimoto's and many others. And I cover how to figure out specific to you what you need to do to optimize your quality of life and your physiology so that you can live a life at optimal.